So let's talk about symmetry of integrands. Let's remind ourselves what an even function means. And essentially with an even function, if we choose a value a and we substitute it in the function and we get out a function value, if we do the negative of that value and we substitute in the function, we also get out the same function value. And an even function then would be symmetric about the y-axis because of this. And if you look at the areas under the curve, you see that they are symmetric. This area equals this area. So if we wanted to, instead of evaluating or integrating from negative a to a, we could actually integrate from 0 to a and then double the area. And why we may want to do that is because it's often much easier to evaluate an integral with a limit of integration that is 0. If you're going from negative 2/3 to 2/3, would you rather substitute 2/3 into some function or substitute in 0? Generally 0 would be easier. So we could integrate from 0 to a and then multiply it by 2. What if the integrand was an odd function? Remember that an odd function, if we put an a in the function and we get out some function value and we put a negative a in, we would get out the opposite sign for the function value. And so this one is symmetric about the origin. And if you look at the areas there, you can see that any area above the x-axis would have a symmetric area below the x-axis. So if we integrated from negative a to a, those areas are going to cancel each other out and we're going to get 0. So if we notice that the integrand's an odd function and we are integrating over a symmetric interval, we can just write equals 0 and we don't have to do any work. So these are summarized. Now f needs to be continuous on this closed interval from negative a to a, needs to be a symmetric interval. If f is even, and this is defining what even means, then if you integrate from negative a to a, that equals integrating from 0 to a and doubling it. And then part B, if the integrand is odd, and then it's defining what odd means there. If you put in a negative x, we would get out the negative of the function. Then if you integrate over the symmetric interval, we will get 0. Let's see a couple of examples then. So here we see that we are integrating from negative 2 to 2, a symmetric interval, and that's the thing that has us thinking about, oh, what about even or odd? Well, this term is even, this term is odd. So I'm going to go ahead and split this up, and I could integrate from 0 to 2 if I double it, x to the 4th dx, and then I could subtract integrating from negative 2 to 2 of 3x to the 3rd dx, but this one I already know the answer is 0 because this is an odd function. So this gets us down to a much simpler thing to compute. I can do the antiderivative here, which is x to the 5th over 5, and we have that multiplied by 2, and evaluate that from 0 to 2. So that's going to be 2 to the 5th is 32 times another 2 is 64/5. And see, we love evaluating at 0 because that would just be minus 0. So there is my answer to that integral. Let's go ahead and do one more. We're going to do the same kind of a thing. So we're going to split this up. Now I think of a cosine function, and we know cosine function looks like this. Cosine function is an even function, so we can double and integrate from 0 to pi over 2 of cosine x dx, and then 4 times the integral of negative pi over 2 to pi over 2 of sine cubed x dx. But we know that sine is an odd function, and then if we cube that, we still have an odd function. So this is going to be 0. Now we just have to compute the antiderivative of cosine, which is sine x, and we have the 2 on it, evaluate it from 0, pi over 2. So that's going to be 2 times the sine of pi over 2 minus the sine of 0, and so we get 2.